three. Yes, ma'am. Okay, this disturbed. Okay, and what it needs memory, flash memory, 16 MB flash memory, 120 MB RAM, 4 GB NAND flash. These are called embedded systems. Embedded system drivers will be there. So we need memory. I need to share data, and these are the memories. Okay. Power amplifier is designed PP58A. What is PP58A? Is a bridge mode power amplifier. This particularly suitable for the generating the power. So bridge mode power amplifier, I am using IC number is PP58A. So you can also design. You can also make it a power amplifier is PP58. So power amplifier chip. So our voltage and restore voltage production is 28 volt DC. My input is the 20. I need to operate this 28 volt DC. Okay, because acoustic more power is required, because in like in RF less power is required, but in acoustic, because we have underwater systems, we need more. So 28 volts is required. Next minute. This is my analog card. Actually, first come to receiving end. This is the receiving chain. This is the transmitting chain. Preamplifier. I have to take care in the preamplifier such that my input to the preamplifier is the transducer, which converts acoustic to electrical energy. So output energy. So acoustic is a piezoceramic element. Piezoceramic is a crank circuit. It has a resonant circuit. So I need a high input input impedance stage in the preamplifier, and it should be able to receiving the all weak signals. The signals coming from the transducer is very weak signal. It is coming from the channel I am converting. So I have to able to pick this. So preamplifier, it will be a preamplifier, a high input impedance preamplifier. Then band pass filter. My frequency of selected band of frequencies, I will select a band pass. This is AD 624. This is AD 624 preamplifier. How can I design it? It is a bit how, I mean, I have to select. I have to see the data sheet and I have to design according to. Okay. This is the band pass filter. This is the AGC, automated gain control. Why I need a AD 8332? Why I need AGC? My signal strength will vary based on channel condition. So I need a automatic gain control. So AGC will be required. For preamplifier, I need sufficient gain to convert into A to D conversion. So I will provide sufficient gain in the preamplifier. Okay, this is the receiving chain. Transmitting chain, reconstruction filter. This is comes from the DT, digital to analog converter. After my modulation, after my programming in programming of the particular data, and it will give to the D2A, digital to analog converter. So reconstruction filter is required. Then driver amplifier, because power amplifier I have to drive. I need a driver power amplifier. This is the AD827 and power amplifier. In the power amplifier, this impedance matching will be required. My transistor is a tank circuit. So what I need a maximum power transfer theorem. I have to the impedance. I am using a transformer in the output of the power amplifier. I have tuned power amplifier such that these two match the resonance frequency of my transistor and power amplifier will match, and I can transmit the set of power. Suppose I transmit my design factor is 180 dB source level. I want to transmit. So I will transmit according to those calculations will be there. 180 dB source level. 180 dB source level means that much of 180 dB I will energy in the hydrophone. Okay. So this is the design, analog card design. Okay, this I have to take care in the analog card design. Okay, next. Next madam, next slide. Yeah, this is the pros card. What it contains? This is the ADC, analog to digital converter. Madam, shall you maximize this, and because screen is not coming properly. Yeah. Thank you, ma'am. This is the ADC. This is the ADC, because what is software defined radio? Software defined radio, only ADC and DAC will be there. Receiver signal from ADC, it will convert into digital signal, and all my processing of the thing will be happened in the processor. And what is DS, and also my modulation parameters, my every software is done by the software. So this is called software defined ADC, processor, and DAC in the SBC card. So I need a memory because I need to store the driver backend. Backend means software. Backend means how program the DBA, how to program. This is comes from the embedded system. How to program the driver software and application software too will be there. Backend driver software will facilitate my A2D, DTA function, memory receiving, memory retrieving. All these things will be provided by the backend. So the memory will be required for data memory, 4G NAND bands, and USB and RS-232 transistor. I want to communicate. I want to communicate with the other processor, other system, other onboard computer system, or it can be a sonar system. Because if sonar data I want to transmit, I need a protocol from sonar to my processor. So this is the protocol. USB or RS both into USB or RS both into is a protocol. So these are the embedded protocol. This is the embedded. So we have to program this backend software. Then this software defined radio programs will come to picture. Software defined radio programs will come to picture. So ADC controller, matched filter and dismissive down conversion, and chip slow keying, demodulation, better bit decoder. For MIMO OFDM, that will be different. One parameter, which module should be in the processor, which module should be in the FPGA. MIMO OFDM, some modules, MRC, maximum ratio combining is the important thing in the MIMO because all channels we have to combine. That will be there. FFT, for this paper is there. How to distribute from the DSP processor and FPGA. How to offload the data, programming in the DSP processor and FPGA for MIMO OFDM. Those things will be, those paper I have available in the Google. I download from the Google only. So like that, what my modulation, what things are happening, I will program this, and I will we custom design in NSTL, our lab, and we are slowly we are working on this. I mean, we have to test this. Okay, this is developed by the Analogic Control Limited, ACL company. They helped in the design. We outsourced the contract with them, and they developed. Next, madam. Hello. Hello.
Yeah, I changed it, sir. I changed it.
Yeah. In now see, this is the PS processing system. This is the PL, program logic. FPGA we are calling PL, and PS FPGA we are calling PS processing system. Some Corel is the firm who is training in the Jing programming. You can contact them, and you can have a session how to do the SDR and MATLAB codes, and also so he is interested to learn this, how to program the software defined radio. Some tutorials also there in Xilinx. How to convert this, how to convert VHDL, MATLAB to VHDL. That is tutorial sessions. So those sections you can learn whenever somebody is interested. You can contact me. Both of let us develop what is there. Jointly we can develop. Okay. This is the what modules. This is the PS. Interleaving, controller, encoding, QPSK, TX, QPS. These are the submodules. What for underwater communication? What my feeling is, what I am thinking is, biomimicry based underwater communication signals we have to use, because all is even the logic modems or OFDM modems are there. So whistles will be there. Whistles means linear frequency modulated signal. Whistles 12 to 24 kHz. I am in 10 milliseconds. I am changing it linearly to 12 to 24 kHz. or otherwise hyperbolic variation will be there. Hyperbolic variation means I will change hyperbolically from 12 to 24 kilohertz in 10 milliseconds. So, and the clicks will be there. In the clicks, phase modulation will take in place. So QPSK kind of things, OFDM kind of things, because these things will happen. Because we have to understand the bio inside wave propagation, then mathematical modeling we have to, then we have to program it. So present available modems, Evologix is successful modem in the world. India, we are not having any modem. We are working on this. So hopefully soon we will get the modem. In our project, Australia DSP com modem is there. They are using. They are telling us spread spectrum OFDM. They are using. They are not, because nobody is revealing their principle. They are telling us spread spectrum OFDM is going there. So what initially the experimental stage, I chosen small easy modules to implement, because if I go to complexity, I will be disturbed. So I mean, practically I cannot do. So slowly, first I developed the FSK modem, and I developed a king modem, and then I will. So now I am working on the QPSK modem, and I mean OFDM, MIMO OFDM also. I am planning. Some collaboration is there. Then we will work on the MIMO OFDM also. So let us see how it will be possible in future. So this is the modem we are telling. This is the PL physical layer I am developing in the PL, because that is not sufficient. I need a MAC layer. I need a MAC layer. I need a MAC layer. I need a routing. Routing will be required, because routing protocols will be required. Network layer protocols will be required. So those things will be, I can program in the PF processing system. In the processing system, there is a multi-core. This is a multi-core system. In a single IC, two ARM A9 processors are there. Two ARM A9 processors are there. So this is a multi-core system. And signal processing stuff is there. Neon processor is there. We can use the neon process. So this is the advantage with the system on chip design. System on chip design is very much useful. Even in a robot, total navigation algorithms, path planning algorithms, communication algorithms, we are working on this. Yeah. So network and routing protocols we can use. We are not programmed. We are not programmed it. This provision is there in this. Okay. This is the analog card. This is the practical modem. We are working presently, and okay. And this is the what I can share from this slide. Okay. Next minute. This is the actually sensor node. Sensor node. I'm in next slides. I am telling this is the present working hardware. This is the ADC, ADC1, ADC2. These are the ADC. We have the okay. This slide I will. You need to understand something about. This is the modeling of artificial underwater acoustic channel. This is the propagation effects will be there, and the reflection. What is the transmission delays and distance, attenuation coefficients, reflection loss. In reflection loss, surface reflection loss, bottom reflection loss. So I am modeling. MSc Prasad is there. One thesis is there. Code is given. Channel modeling is given. You can work on this in the MATLAB, and this is the propagation delays. So this is the bound. Suppose this reflections is different. Some rock, some reflection coefficient will be different. If salinity is different, then temperature is different. So these are called bathymetry parameters, ocean parameters. For each individual parameter, impulse response. FSK modem. After I done trials, then I realized no practical demonstration. We need a channel model. We need a model. Everything I cannot test. I worked. We modulate the modulated signals we give to channel model. Channel model which are available in the internet. I will guide you if anybody is interested. Okay, next one. Next. Yeah, I in the channel model I developed meters, depth is 300 meters. I transmitted a 100 millisecond pulse width in the channel model, and the receiving I received pulse output of the channel I observed. So 100 meters no effect. This is 34 for different depths, for different geometry of the parameter. If I change my pulse width, then what is the effect? What is the propagation effect I studied? So
ఎడబెట్లో సార్ వైట్ పేపర్లో అవునా
this is at
దేనికి
my transmit pulse width of 3.3. I have 4.2 milliseconds, 3.8 milliseconds. Madam, I crossed the time now. Okay.
Yes, sir. Our session is actually till 3:30.
Yeah, yeah. This is the result I propagated and received. See the fading in the signal. Next. Modulation I experimented in the ocean, and what I observed is simulations and tank tests. We have tank tests also, so there is difference in there. Okay, this is the tank test I have done. Okay, this is the modem. We developed a DDS 9834, and this is the receiving chain FPGA. What I have discussed. This is the software. We can control the parameters from the FPGA, power amplifier, receiving chain. Okay, this is the what we have developed. Okay. Okay, next. Okay. This is the experiments what we have discussed. This is the channel model. This is the impulse response for this shallow water. This is deep water. See, the difference is there. And this is the propagation. This experiment. This is the what we transmitted data. Hello NSTL. Hello NSTL. So this is the ASCII data. So we transmitted and decoded successfully with up to 100 bits per second. Not more than that. In the harbor we tested, we get up to 1 H only, 1 bits per second only. We transmitted. We are able to receive the data. This feature we will hope we will investigate. Okay, man. Next, man.
Sir, a small question, sir, here.
Yes, madam.
Sir, when you identify the pulses, the previous
Okay.
slide, that spectrogram, did you
Okay.
use wavelet, sir? How did you identify the pulses? Like four
no, I
pulses.
am not using this madam.
Yes, sir.
This madam.
Yes, sir.
This is the MATLAB code given in the model. I am not estimating. This is not estimation. This is the mathematical equations. I am plotting this one.
Okay.
Borowski is the one thesis is there. In that he correlated and estimated the channel. This is the channel, is not a channel estimation. This is the propagation effects. Directly, I am plotting in a time frequency domain. So here it is one delay. This is another. This is the one ray. This is one ray. This is one ray. The mathematical equations I am in the MATLAB. I am modeling and getting these equations, propagation effects. This is not the estimation.
Oh, no, sir.
Okay, madam.
When we see that actually a single line in that CRO refers that we have identified
this one, madam. This one.
Pulse.
This one is the coded ping pulse modulation, madam. What I done is practically 10 milliseconds. Suppose in a school bell, ting 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 ting, gap will be there, madam.
Yeah.
Okay, like that. I 10 millisecond. I coded pattern. I modulated 10 millisecond on, 0.5 second off. 10 millisecond on, 0.5 second off. Okay, are you following?
Yeah, yes.
In my DDS, I program like this. I decoded. After receiving and I will decode it. These are the decoding. Receiving after demodulation, I decoded these things. Okay, madam.
Okay, sir.
This is the practical waveforms. This is like what medium. Suppose my sensor node, because after seeing this complexity, I have to freeze my project, because my project will not wait for my research. I have to something fuse it, and next version I have parallelly I have to develop. I have to give, because this such much of complexity is there in acoustic communication. So what I designed is simple coded ping pulse patterns. This pulse data acquisition on, this pulse data acquisition off. Like that, I programmed. Okay, madam.
Yeah, sir.
3 ping pulse, data acquisition on. Lapate record on. I will send 5 pings. Record on. Record will my processor in the SBC will take care of the recording on. So like that I programmed. This is coded ping pulse. This is indigenous. Nowhere it will be there. Chirp signals nowhere it will be there. We are programmed. In RF you can things. In underwater we programmed.
Okay, sir.
Okay, madam. Next one. I thought I will go to sensor network. This is okay. This is software dependent. Already I discussed. This is the Jink modem. Already I discussed. Okay, madam. Okay. Okay, madam. Thank you for your patience. Next, if some time is there, I will discuss sensor network in the next version because time is not there. I thought wireless sensor network also I want to discuss if time permits, but time is not there. Hope we will meet again and we will discuss on the wireless sensor network in next module or next phase. Anything is there. Okay, madam. Thank you very much for hearing my patience. Thank you very much, everybody, audience. Wish you all the best. This is the age. If you, from DRDO, I wish you all the best.